Okay. What we're going to discuss in this video is the pressure in a fluid of uniform density. Yun bang ang isang fluid, yung density niya is uniform all throughout. Okay? So in our previous video, we derived this expression, this one, the P sub 2 minus P sub 1, meaning the varying pressure at different levels or elevation at y sub 2 minus y sub 1. Okay? So we derived this equation in the previous video. We discussed how we come up with this expression. Okay. Now this expression is used to describe pressure in terms of depth below the surface of the fluid. Ibig sabihin, that describes pressure in a different elevation inside the fluid. Okay? So there is a change. Okay? There is a change of pressure as we move up and down, okay, inside the body of the fluid. Okay, for example, in a liquid. So if we're going to go up, okay, or if we're going to reduce our distance from the surface of the liquid, of that fluid, the pressure also changes. If we're going to go deeper, okay, kung pupunta tayo sa malalim, the pressure is also changing. Okay, that is what we mean by this expression. So this expression tells, okay, that particular observation. Okay. Now, we are going to use this expression to analyze the difference of pressure when it is at the surface, okay, and when it is at the bottom or at particular any elevation inside the fluid, for example, a liquid. So, look at the illustration we have here at the left side of your PowerPoint, of our PowerPoint, I mean. So, P sub 1, meaning we are referring to that particular point where the pressure is found or measured at this particular point. Okay? So, we assume that this pressure is higher, okay, higher compared to the pressure that we can measure above this particular point. Okay? And P sub 2 as the pressure above the surface of the fluid or of the liquid. Okay, because in this example we are using the liquid. Okay, so the change of elevation is simply referring to the h or the height. Okay, so that is why it is y sub 2 minus y sub 1, referring to that elevation where the point 1 is found. Okay, here. Right? So, we could express P sub 1 as the pressure inside the fluid in a particular given elevation or the H. Okay? So, P sub 1 is equal to that particular pressure. And the P sub 2 is the pressure that we can measure or we can get from or at the surface of the fluid. That is why here I have this expression P sub 2 referring to the pressure that we can get at the surface of the fluid. Okay? And the H here, simply itong y sub 2 minus y sub 1. Okay? At any point, okay, take note, at any point of the elevation or any elevation inside the liquid or fluid. Okay? So, we can rewrite this particular expression that we derived in the previous video in this way. Alright? So, P sub 2 becomes P sub 0 That is the pressure at the surface of the fluid minus the pressure, okay, okay, inside that liquid or fluid equals negative density times the gravity times y sub 2 minus y sub 1, meaning the h, or we can rewrite that as negative density times the g, or the gravity times the height. Okay? So, we will arrive with, okay, we will just going to eliminate this particular expression because this expression is actually this one. Okay? The y sub 2 minus y sub 1 here is actually the h. So, we will not anymore use this particular mathematical expression here. So, we could express it like p sub 0 minus p equals negative density or minus density gravity times the height. Okay? I hope that is clear. So, if we're going to rearrange the formula or the equation, we will arrive with pressure is equal to the pressure at the top of that surface, or at the surface, I mean at the surface of the fluid, plus the product of density, the gravity, and the height. Okay? Now take note that this expression, the rho, gravity, and the height, is actually referring to the weight force. Okay? Weight force. Because we understand that at a particular column here inside the liquid, okay, we can get the weight, okay, the weight of the fluid, okay, by looking at its density, the height or the elevation where it is found or we are measuring, and of course the gravity, which is 9.8 meter per second squared. Right? So this expression, the density or the rho times the gravity times the height, is actually the weight force. Take note of that. The weight force of the liquid or the fluid that we are measuring. Now, why is it that there is P sub 0 at the top? Okay? Because if you're going to remember our previous discussion about the total pressure, the absolute, and the atmospheric pressure. Okay? Here, we integrate or we consider, okay, the pressure that the atmosphere is exerting on the surface of the fluid. Okay? Which is 1 atmospheric or 1 atmosphere. Okay? That is why we have this quantity or this P sub 0 in this equation. Okay? So if we're going to look at this expression here, it is just similar with our formula that we discussed earlier about the total pressure that is equal to the atmospheric pressure plus the gauge pressure. Okay? This is just the same expression. Right? So what we're just going to, what we are referring here is only that the pressure, okay, inside the system or inside the fluid, which is called the gauge pressure. Right? I hope that is clear. So let's proceed. Okay, now. So, as what I've said well ago, that the pressure inside the fluid, okay, is always greater than the pressure that is found at the surface, okay, of the fluid or of that liquid. Okay? So meaning the pressure, okay, inside or below or in that particular elevation at height, no, at a particular height, okay, below the surface of the fluid, okay, is always greater than this particular pressure, okay, at the top, okay, at the surface of the fluid. Okay, take note that in a particular given amount of density, okay, because if the density is if the density is different, for example, if we're going to compare liquid, water with oil, the density is different. Okay, like for example, we consider the same elevation. Okay, pareho sila ng elevation. However, the density is different. So the pressure is directly proportional. As you remember, that the pressure is directly proportional to the density. Okay, don't forget with that. So if the density is bigger, okay, or big, no, compared to the other types of fluid, meaning the pressure is also different. Okay. Now we have to remember, okay, that pressure, okay, pressure acting at the particular level, okay, the pressure that we can get at that particular level, okay, the same level is equal, okay, the same amount of pressure, okay, or the same magnitude of pressure. So the pressure is the same at any points at the same level of fluid. So if what pressure that you can get from this point here is the same if we're going to measure it here, okay, at this particular container or formation of cylinder, and the pressure is the same here and also in this particular cylinder, okay. And if we're going to measure the pressure at the bottom, okay, of this device, the pressure is the same if we're going to measure it at this particular point, at this point, or any point, okay. Meaning, the pressure is the same. But if we're going to go deeper or downward, okay, for in the fluid, the pressure is not the same. Okay, so it somehow increase as we go deeper to that body of the fluid. However, if we're going to measure the pressure horizontally, okay, the pressure is just the same. Okay, that is why, as you observe here in the picture, the surface or the film of that surface is just at the same level. Okay, because we are going to consider also the atmospheric pressure that acting at the surface of the liquid here. Okay, so the pressure, the atmospheric pressure here is the same. The atmospheric pressure that acting inside this particular tube is the same. Also here and also this particular part of the device, the atmospheric pressure is just the same. That is why we have the same pressure distributed in this particular manner, okay, in horizontal, okay, manner. Let's proceed. Okay, so we have here again the illustration. So if we have pressure at A here, no, or P sub A, okay, and then we move to P sub B, the pressure from this point going to that point horizontally is just the same. That is why the P sub A is equal to P sub B. Okay, it's just the same. All right. Okay. Then that is also the same with if we're going to go deeper to that part of the fluid. So, for example, P sub C or PC, the pressure at this point is the same if we're going to measure the pressure at that particular manner, no, horizontal. However, we assume that the pressure that we can get from here, from this portion, is different from the pressure that we can get at the top. Okay, that is why if this is pressure 1, okay, and this is pressure 2, we always assume that pressure 2 is greater than the first pressure. Okay, again, the second pressure, which is found at the bottom here, the second one at the bottom, is greater than the pressure that we can get from this point. Okay? Why is that so? Because again, that is because of the weight force. Okay? That is influenced by the density. Okay? and the gravity. Okay? So the pressure only varies depending on the height, okay, or elevation, okay, inside the fluid. Okay? That is also expressed by this particular mathematical expression here. Okay? The differential. Okay? So meaning, the pressure change is changing. Okay? The magnitude of pressure is changing if the elevation is changing. Okay? And we assume that the density, because we are talking at this, because we are talking of the same fluid, so the density must be constant. Okay? In different parts of that particular fluid, constant, the same. Okay? And of course, the gravity is the same. So this part is constant. So what is just changing is the elevation, or the dy. Okay, that's why we have the differential symbol here. Okay, dy, or the y, or the elevation, and the pressure. So if the elevation is changing, the pressure is also changing. Okay? And at this point, it's important that we have to understand this, what we call Pascal's law. Okay? That says the pressure applied to an enclosed fluid, okay, is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. Meaning, if you are going to apply force, okay, perpendicular to the surface of the fluid, okay, considering that the container is the fluid is enclosed in a particular container, the force is, or the pressure applied is distributed all throughout, okay, at the different portion of the fluid. Okay? Now, let us talk about the force. Okay, now what about the force? What will happen about the force? Now take note, if we have a fluid that is at hydrostatic equilibrium, okay, meaning, if we will say at hydrostatic equilibrium, the forces are balanced. Okay? If we will say that the forces are balanced, meaning the net force is equal to 0. Okay? Take note of that. So, for example, if we are going to put a particular film inside the fluid, okay, what will be the force? What will be the magnitude of the force? Take note, it is at hydrostatic equilibrium. What is the magnitude of the force, okay, coming from this direction and also opposite to that particular direction? Okay? Given a particular area, or the dA. So, if it is at hydrostatic equilibrium, the force is equal. Okay? So, dF sub A is equal to dF sub B. So, what will be the magnitude of the force of the FA here will be the same with the magnitude of the force coming from this particular direction. Provided, again, that the fluid is at hydrostatic equilibrium. Okay, hydrostatic equilibrium. Now, if it is in motion, this will never be equal. It could be that the force at this particular point is greater than the other part of the fluid, if it is in motion. Okay? However, what we are talking here is that the fluid is at hydrostatic equilibrium. Okay? Now, this is in horizontal manner, right? Now, what about if we're going to look at the forces acting in the vertical pattern or in a vertical manner? Okay? So, that is the same. They are the same. Okay? So, for example, at this particular point where the two arrows meet, okay? If what will be the magnitude of the force going downward at this particular point, that is also the same force that is acting against that particular point. Okay? Here. They are equal. Okay? Okay. Now, if we're going to go deeper, for example, at this point, go deeper, no. So meaning, um, uh, the force here, okay, will be greater than the force that we can find at this particular portion. However, the force going downward, or the weight force, okay, the magnitude of the weight force is equal to the normal force exerted by the fluid, okay, from the bottom, right? Meaning, the force that we are talking here in the hydrostatic equilibrium of the fluid is a point function. Okay? So, the pressure gradient force is balanced by the gravitational force. Okay? That's as what I've mentioned a while ago. And this balance ensures that the fluid remains stable and doesn't accelerate. Okay? And the pressure gradient compensates for the weight of the fluid column above the certain point. Okay? So, do not be confused, because if in some other references, if you see P times A, okay, that is the same with, that is actually force. Okay, don't be confused. So, in this illustration, what I use is directly the F. Okay, but also, in some other references, you will see that it's not F, but they use PA, or the pressure times the area. Right? Okay, now let's proceed. Okay, again, Pascal's law states that pressure applied to enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. So we have the illustration here at the left side of the PowerPoint, or of the slide. Okay, so in cylinder 1, okay, this is the expression force F1 over A1. Okay, for cylinder 2, this one, F2 over A2. Now, take note that you might be experiencing some confusion, because this particular force exerted here, of course, is greater, no, compared to the F1 here, no, that is only a cylinder or something, or a solid cylinder put at a particular point. Okay, so but according to Pascal's law, that the pressure, okay, take out the pressure inside the fluid is equal. Okay, if we're going to remember our previous discussion about the fluid as a continuum, meaning the fluid here act as a single body. Okay, it act as a single body. Ibig sabihin, the force that you applied here, okay, or the pressure, okay, the force that you applied here, okay, will be distributed all throughout the body of the fluid. Meaning, the pressure that the fluid is exerting at this particular cylinder will be distributed to this particular cylinder. That is why we have the expression that P is equal to F sub 1 over A sub 1, and equals F sub 2 over A sub 2. Okay. So if we're going to look at the magnitude of the force, or of the second force, we can simply rewrite the expression. So we can have force, or the second, F sub 2 equals A sub 2 over A sub 1 times the force, or the first force. Okay? So take note of that. So that is the Pascal's law. So again, the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. So what will be the pressure reading here? Okay, is the same if we're going to look to have a particular reading of the pressure here. Okay, so at this particular portion, if what will be the reading of the pressure here is the same. Okay, it is distributed undiminished. All right. Okay. Now, for gases, we have the assumption that the density is uniform. However, for gases, that is only true if it is at a short vertical distances. Right? Okay. So, we have here the example, the ceiling and the floor that is actually 3 meters away, no? And the density of the air is 1.2 kilogram per cubic meter. So the pressure, okay, that we can get at the floor is 35 pascals, or that is approximately 0.0035 atmosphere, right? And this difference is negligible, no? We can consider this one as negligible, okay, at that particular distances. Take note that if we're going to compare 3 meters to the height of the Mount Everest, this is just so small, very insignificant. Okay, so in this particular difference, the 3 meters, the short vertical distances, we can still use the assumption that the density is uniform. Okay, but this assumption that the density is uniform is not anymore applicable if we're going to measure the density of the fluid or of the air, okay, if we are comparing already very long distances. Like for example, in Mount Everest, that the peak is about 5,200 meters. So the density of air at the peak is not the same with the density of air that we can get from this particular level, and also when it is at sea level. Okay, so the assumption of density as uniform, okay, is not anymore valid in this particular condition. It is only valid if the vertical distances is short. Okay.